we're going to do is use area models and tree diagrams to work with some, I guess, real life types of problems to get this figured out. So we'll see kind of what happens here. So rock, paper, scissors. I always say rock, scissors, paper, and everyone always makes fun of me. So your team will play a variation of rock, paper, scissors, sometimes called Rochambeau, and record points. You will need to work in a team of 4, have one person act as recorder while the other 3 play the game. So list the names of the people in your team alphabetically, so we'll just have player A, B, and C, and the 4th is recorder A. Write down who has each role. Without playing the game, discuss with your team which player you think will receive the most points by the end. A gets a point every time all 3 players have the same. B gets a point every time 2 of the players match. And C gets a point each time nobody matches. So now play rock, scissors, paper with your team at least 20 times, and let's see who would win. So obviously we're not going to be able to play 20 times, but we can do D, calculate the probability for each outcome of whether A, B, or C will get a point. So again, what would be good for you to do is just do a quick guess who you think will win, A, B, or C, and then we'll figure out the probability. Typically, it goes to form, and you'll see what I mean in a second. So the question is, would it make sense to do an area model, or would it make sense to do a tree diagram? And I know some people prefer an area model, but a tree diagram is a lot more flexible if you have more than 2 things going on. And what do I mean by that? Well, here's exactly what I mean by that. If we wanted to make an area model here, we would say, all right, well, player 1 is either going to throw, a rock, a paper, or a scissor. And then player number 2 is going to throw a rock, a paper, or a scissor, right? And that's the area model right there. But the problem is we have a 3rd person. So where would we put number 3? We can't go left and right. We can't go up and down. It would actually literally be forward and back, like 3D coming towards you. We would have to make it a cube. And at that point, what we could do is we could say, here's player number 3. They have a rock, a scissor, or a paper. And then we have this cube. And it gets pretty complicated pretty quickly, right? Now we're looking at this cube here. And, this part of the cube is player 1 throws a scissor, and player 2 throws, a rock. And then player 3 throws paper, whatever it might be. But what if we... Even then, we can make it happen. We can do 3D if there's 3 people playing. But what if there's a 4th player playing? Then we run out of dimensions, right? So all of a sudden, that will no longer work for us. So that is one of the limitations of a area model. And I hope I am making myself clear, because I know it's a little bit confusing. But one of the limitations of an area model is that you can really only have 2 things going on. When you get into 3 or 4 or 5 things, you can do a tree diagram. Now, I will say there is actually ways to combine like player 1 and player 2 and use a area model, but it's kind of complicated, and I think a tree diagram is definitely the way to go. So we're going to make a tree diagram of this. Again, I think I'll pause so you don't have to sit through it. Over the years, I've always had kids get a little bit confused by this tree diagram, so hopefully you guys are with me on this. So this is player A. Actually, I should make these A, B, and C. My mistake. So player A is either going to throw rock, paper, or scissor. Now, if they're playing for real and not cheating, it shouldn't matter whether they throw a rock, paper, or scissor, because player B is going to throw a rock, paper, or scissor. And then again, player C, it shouldn't matter what A and B do. They should throw rock, paper, scissors. So in terms of being able to read this graph, it's really important that we can. So if I end up right here, what this means is player A threw a rock, player 2 threw a scissors, or player B threw a scissors, and player C threw paper. If you end up right here, that means player A threw scissors, player B threw scissors, and player C threw scissors. So I hope we understand how to read these tables, because it's really important that we understand what's going on here. And I know it looks like C is throwing a lot more, but it just depends on what A and B do as to how we read this, because what we're really saying is A could throw rock, paper, scissors. Pause for a second. Okay, sorry about that. I'm a loud ringer. So A could throw rock, paper, scissors. B could throw rock, paper, or scissors. But B throwing rock, paper, scissors is happening no matter what A does. And C throwing rock, paper, scissors happens no matter what A and B do, right? So that's why it gets so big so quickly. So let's figure out who gets points. So A gets a point if all three match. So if they all throw rock, player A matches. If they all throw paper, player A wins. If they all throw scissor, player A wins. Player A only is going to win 3 out of 27 times, right? There's 3, 6, 9, 12, 15, 18, 21, 24, 27 ways. So player A isn't going to win very often. Player B gets a point if 2 of the 3 players match. Well, let's do player C. C gets 1 when no one matches. So rock, paper, scissor, player C would win. Rock, scissor, paper, player C would win. Paper, rock, scissor, player C would win. Paper, paper, well, C can't win here. Paper, scissor, rock, player C is going to win. Scissor, rock, paper. Scissor, paper, rock. And then scissor, scissor can't win. So 1, 2, 3, 4, 5, 6 out of 27 ways. So hopefully we already realized that I better get 18, right? 9 plus 18 is 27. Now let's make sure that's correct. So 2 of these 3 should match. There's 2 rocks. There's 2 rocks here. Rock, paper, rock. Rock, paper, paper. Rock, scissor, rock. Rock, scissor, scissor. Paper, rock. So you can see as we go through this that there is indeed 18 ways for B to win. So those are the odds. So this is what's going to happen. Now it says, describe a plan to make this game fair. Well, here's where money always makes this a lot easier, or a point system makes this a lot easier. What if we said, all right, here's what we'll do. Every time player A wins, because they shouldn't win very often, every time player A wins, we'll make it worth 6 points. So the 3 times they win times 6 points each, they're going to get 18 points if you play 27 times on average. Player B will make it worth 1 point. So if they say play 27 times, they'll win 18 times 1 point. That would be 18 points. And then player C, well, what if we make this times 3 points? They play 27 times, player C wins 6 of them, times 3 is 18 points. So if you go with like a point scale where you give more points for the things that happen less often and less points for the things that happen more often, that might be a nice way to make this fair. Game at the school fair called Pick a Tile, in which the player reaches into 2 bags and chooses 1 square tile and 1 circular tile. The bag with squares contains 3 yellow, 1 blue, and 2 red squares. The bag with circles has 1 yellow and 2 red circles. In order to win the game and a large stuffed animal, a player must choose 1 blue square and 1 red circle. Explore this game using this tool. So let me set that up. Basically just click it and it'll spit out tiles for you, and then you can decide if you win or not. I think you need a blue square and a red circle to win, so that would be a loser. There we go, blue square and red circle, so we got a winner right there. Okay, so now it costs $2 to play this game, and Marty and Jerry decide to calculate the probability of winning before deciding whether to play. Jerry suggests they make a systematic list of all the possible color combinations in the sample space, listing squares first, then circles. So you can have a red square and a yellow circle, a blue square and a yellow circle, a yellow square, a yellow circle, etc. So Jerry says there's a 1 in 6 chance of winning. Do you agree with Jerry's answer? I would say no. I disagree. It doesn't take into account the odds, right? There's more yellow squares than there are blue ones and red ones. It doesn't take into account that some squares or circles colors happen more often, or there are more of them, right? So it says make a tree diagram for this situation. Remember to take into account the duplicate tiles in each bag. So this is going to be kind of interesting because I'm going to make two of them, and I'm going to pause this, but I want you to see the difference between the two. Two completely different tree diagrams, but you can see they both have the same odds of winning. Again, to win, you need to get a blue square and then a red circle. So on this one, I just went ahead and I know there's 6 tiles in the bag, right? So there's 3 yellow, 1 blue, and 2 red. And then on this one, it doesn't matter what you pulled out of the square bag. Then you go to the circle bag, and it's either 1 yellow or 2 red. So the only way you win is if you get a blue square and then 2 red circles. And there's 2 out of 18 ways to make that happen, or you have a 1 in 9 chance of winning. Now, the square, again, you can see it's the same information. 3 of these 6 are yellow, 1 of these 6 is blue, and 2 of these 6 are red. From there, you're either going to get a yellow or red. 1 of the 3 is yellow, 2 of the 3 are red. So I get the same thing. And again, to win, you need to end up right here. 1/6 times 2/3. And obviously 1/6 times 2/3 is going to equal 218. So I don't care which way you set this up. You can just put every single possibility, list every single possibility, and then just count. Or you can use these odds and multiply the odds, and you get the same answer. Now the question is, should they play the game? Well, they should win this game 1 out of every 9 times. It costs them $2 to play the game, right? So you're really looking at it costing, you would expect to win after $18, right? Because you should play 9 times before you win. And you would expect to have to pay $18 to win the game. So that's the question. Is this stuffed animal worth $100? If it is, you should probably play this game because you're going to win a $100 stuffed animal more than likely. You might not ever win it, but more than likely for a lot less than it costs. If the stuffed animal costs like $5, it's probably better off just going to the store and paying $5 because you'll probably spend more than $5 to win it. So that's some of the logic that goes into these probability type questions. This up, I went ahead and just kind of did the same thing and used the common denominator fraction. So to get a yellow, it's a 3 out of 18 chance. To get a yellow red, it is a 6 out of 18 chance. And I noticed I didn't actually go to all this trouble for the area model. So I apologize. But I only figured out the odds of winning on that. So here, it's a 1 out of 18. Here, it's going to be 2 out of 18. And again, I'm just multiplying the 1 by the 2 and putting it on top, and the 6 by the 3 and putting it on bottom. And again, here's our winner right here, 2 out of 18. So you can see it's the exact same information. And then you're going to lose 16 out of 18 ways. 3, 9, 10, 12, 16 out of 18 losers, 2 out of 18 winners. So it says use the probability area model to calculate the probability of each possible color combination of square and circle tile. Explain to Marty and Dre why the probability area model is called an area model. Well, obviously it's done by area, so this area is this times this, whereas this area is this times this. It says discuss which model you preferred using the pick a tile problem with your team. So I don't know, maybe you preferred the tree diagram, or maybe you preferred the area model. Let's say area models are typically cleaner to keep organized, in my opinion. But like we mentioned, like we have right here, could you have used an area model for the rock, paper, scissors? I would say no. So in my opinion, again, and that's because you run out of dimensions, right? So I think an area model is cleaner, and I kind of like the setup, but I think the tree diagram has more flexibility for sure once you get past 2 decisions, like 3, 4, 5, 6, 7. The area model really has limitations, but the tree diagram doesn't. You can just keep going forever with that. Shooting 1-on-1 free throws. So Rimshot McGee has a 70% free throw shooting average. The opposing team is ahead by 1 point. Rimshot is at the foul line in a 1-on-1 situation with just seconds left in the game. A 1-on-1 situation means that Rimshot shoots a free throw. If he makes the shot, he shoots another. If he misses the first shot, he does not get a second shot. Each shot made is worth 1 point. So first, take a guess. Who do you think is most likely outcome for Rimshot? 0 points, 1 point, or 2 points? So draw a tree diagram to represent the situation. And then it says Jeremy is working on the problem with Jenna, and he remembers that area models are sometimes useful for solving problems related to probability. They set up the probability area model right. Discuss with your team which part of the model represents getting 1 point and 2 points, etc. So then what we're going to do is use the tree diagram or the area model to help you calculate the probabilities that he will get 0 or 2 points. What's the most likely of the 3 outcomes? So the reason why I did that is because I wanted to read ahead, because I'm going to have these two right next to each other. So essentially what we're going to do is I'm going to make a tree diagram on the left, and then we're going to have the area model on the right. And we'll just compare and make sure they have all the same information, and then everything's okay. So the first shot, so this is shot number 1. He's going to make it 0.7. I don't like using percents. I like using decimals. So hopefully we're okay with moving that decimal point 2 spots and coming up with 0.7. So that means he's going to miss it 30% of the time, or 0.3. If he makes it, he gets to shoot again. And again, that means he's 0.7 to make it. He's 0.3 to miss it. And over here, I don't need to keep going, because if he misses the first shot, there is no second shot. So now we go through, all right, well, what are the odds of this happening? So the odds of him making 2 in a row are 0.7 times 0.7, which I'll tell you right now is 49%, but I'll show you just in case. So 0.7 times 0.7 is 49%. So there's a 0.49 or a 49% chance that he'll make both and get 2 points. There is a 0.7 times 0.3, which is again 21%, but I'll just show you what it looks like on the calculator. There's a 21%, 0.21, move it twice, 21% chance that he'll get 1 point, because again, he gets 1 point for a make and then a miss. But there's a 30% chance, there is no second chance, right? If he misses, that's it. There's a 30% chance that he'll get 0 points. So what's the most likely outcome here? Well, it looks like the most likely outcome is he'll get 2 points. So let's take a look. 0.7 times 0.7 is 49%, and that would be 2 points. 0.7 times 0.3 is 21%, and that would be 1 point. And 30% chance that he'll get 0 points. So you can see it's the exact same setup over here. So whether we use the tree diagram or whether we use the area model, we assume that he will make the 2 points most often. Ironically, even though that's the most likely thing to happen, it's still less likely to happen than these two combined, right? The most likely thing would be that he doesn't, well, how do we say this? The most likely thing is that he'll score 2 points, but that happens less than half the time, which is kind of weird, but hopefully that makes sense. Statistics can be a weird thing sometimes. One thing I will mention again is the flexibility of an area model, because of a tree diagram, because if he took a third shot, we'd just put it down here, right? But here, we've run out of places to put a third shot. Again, it would have to be 3-dimensional to do that third shot, which would make it a little bit tricky. Well, I didn't mean to close that, which is a bummer. But we will go ahead anyway. I think I'm done with this problem, and I will pause and we'll finish up this lesson. Last questions. It says, with your team, examine the probability area model from problem 326, which looks like this. What are the dimensions of the large rectangle? Well, it's 0.7 times 0.7, so it's 49% of the total thing there. And explain why these dimensions make sense. Well, I think they make sense because that's the odds of him making a percentage, right? So it's 0.7 by 0.7 makes sense because those are the odds of him making free throws. All right, so it says, what is the total area of the model? Well, the total area of the model is going to be 1 times 1, right? 0.7 plus 0.3 is 1. 0.7 times 0.3 is 1, so 1 times 1 is 1. So the total area equals 1. Or 100%, right? Don't forget that 1 is a percent, is 100%. Express the area of the product of the dimensions as the sum of the products. So yeah, I'm not really sure what they're getting at here. I think they're probably saying something like 0.7 plus 0.3 times 0.7 plus 0.3 equals 1. So again, like 0.7 times 0.3 times 0.7 plus 0.3 equals 1. And it says what events and probabilities are represented by the entire area model. Well, the two things that can happen, the three things that can happen are 49% of the time is make, or 2 points. 21% of the time we have a make, miss, which is 1 point, and 30% of the time is a miss, which is 0 points. So that's the entirety of the 100%. If you add that up, you'll get 100%, which is the total. I think they're just trying to make the point that we have all the possible scenarios here. And here's our kind of our systematic list. You can make, miss, or you can miss. That's all you can do. I hope this makes sense. I know these lessons take a while to get through, but I'm trying to go slowly just to make sure. I know over the years kids have had a lot of questions on these, so I'm trying to answer those questions as I go through, so hopefully that makes sense. Reach out if you have questions, of course.